It's a pleasure, honor, always to be here. Today I'll be talking about joint work with Ian Smythe, which we've labored at for so long that I hesitate to even term it recent. The paper's over 100 pages, and it will post within weeks. And I want to try and tell you what's in it. There's a sense also in which this paper is about what isn't in it, by which I mean the following. This work is foundational in conception and character. It records a framework we like to imagine for works well beyond it, by hands and collaborations well beyond our own. Framing it is a mystery. A curiosity of the enormous, was there a question? A curiosity of the enormous advances in the fields of manifold classification and invariant descriptive set theory over the past 40 years has been their comparative lack of interaction. We can hardly attribute this, for example, to any inherent antipathy between manifold theory and logic. Against the background of the extensive literature interrelating manifolds and computability theory, in fact, this curiosity grows all the more striking. Add to this, not only invariant descriptive set theory's programmatic interest in classification problems throughout mathematics, particularly in manifold adjacent fields like dynamics, work of Foreman, geometric group theory, work of Thomas or Szabolcs or Calderoni, but Hjorth's framing, add to this Hjorth's framing in one of the field's foundational texts of the classification of compact surfaces as among the most exemplary of solutions to such problems, and we have the makings of a positive mystery. What do I mean by Hjorth's framing? This is a foundational text. This is how it begins, and its first example of a successful classification is of surfaces. This book's about 30 years old, and I feel like we should have more results on classification of manifolds. I'll talk about the ones that I know. But overwhelmingly, for me, the impression is of a lack. And the purpose of our paper is to begin to remedy this lack. And this involves, naturally, identifying one of this mystery's likely culprits. A few sample theorems will help to suggest the benefits of remedying this lack. Consider, for example, the following. There's a theorem by Markov, 1958. There exists an effective map M from the class of finite presentations P of groups G of P to the class of compact four manifolds that takes a presentation, turns it into a manifold, whose fundamental group is the group that presentation presents, with the property, moreover, that two manifolds are homeomorphic if and only if these two presentations present the same group. This M, this map, reduces the recursively unsolvable group isomorphism problem to the problem of classifying compact four manifolds up to homeomorphism. This theorem is well known to manifold theorists, I think. And it carries the folkloric corollary that the latter, in other words, the classification of compact four manifolds up to homeomorphism, is quote unquote impossible. But this inference should be handled with care. For we have, in contrast, the following. Theorem A. For every positive n, both the classification of compact topological n-manifolds up to homeomorphism and of compact smooth n-manifolds up to diffeomorphism, each of these classification problems is Borel equivalent to the equality relation on the natural numbers. In particular, from an invariant descriptive set theoretic perspective, the classification of compact four manifolds up to homeomorphism amounts to the simplest of all infinite classification problems. By infinite, I mean with infinitely many classes. This is, of course, compatible with a view deriving from Markov's theorem of classification of compact four manifolds as hard, but only alongside a view of classification problems generally accredited as solved as being even harder. The degrees appearing in the following theorems, for example, form a strictly increasing Borel reducibility chain above equality on the natural numbers. If you don't know the benchmarks that we've seen these in the course of the week, but the main thing is just that the degrees are going up, the complexity is going up. Theorem B The classification of complete hyperbolic two manifolds with finitely generated fundamental group up to isometry is Borel equivalent to the equality relation on the real numbers. Theorem C, the classification of, just change out 2 for 3. The classification of complete hyperbolic three manifolds with finitely generated fundamental group up to isometry is Borel equivalent to the relation E0. This is maybe the most surprising of these theorems. Theorem D, the classification of complete hyperbolic n-manifolds up to isometry is Borel equivalent to the degree E infinity. It's essentially countable universal for any n greater than or equal to 2. Theorem E, the classification of surfaces up to homeomorphism is complete for countable structures. Same if you move to the smooth category, smooth two manifolds up to diffeomorphism. Complete for countable structures, put differently, each is complete for orbit equivalence relations induced by Borel actions of the infinite permutation group S infinity. Now, the apparent tension of these theorems with the implications of Markov's is, of course, ultimately illusory, for they involve different registers, while the latter derives its force from the question of whether the isomorphism problem and its resolution with finite resources, the underlying concern in the former, for invariant descriptive set theory, is for what is or is not achievable with countable resources. The real point here is that this distinction between these two lenses manifests in turn as follows. One value of the Borel complexity framework is its description of a finer and more definite structure of quote-unquote degrees of difficulty within the study of manifolds than has tended to be perceived. Extending this point is one outstanding exception to the comparative lack of interactions between manifold classification and Borel complexity theory cited above, namely Hjorth and Kechris's the complexity of the classification of Riemann surfaces and complex manifolds. We'll note other major exceptions shortly, but they are few. In that paper, motivated by questions coming from outside of descriptive set theory, motivated by questions regarding the complexity of conformal invariants, the authors show the following. The classification of Riemann surfaces up to biholomorphism is Borel equivalent to the degree E infinity. So this sort of coincides with our theorem D. Our theorem D in some ways extends it to higher dimensions. 2, for any n greater than or equal to 2, you have a turbulence result. The biholomorphism relation on complex n manifolds does not admit classification by countable structures. I highly recommend this paper. It forms our own work's principal inspiration. But I would also note that roughly 9 of its 34 pages are taken up with what its authors termed the technically cumbersome, although mathematically rather shallow, business of parametrizing its objects of study. And I do so for what it suggests of at least one of the culprits behind the, quote, mystery framing our work. It seems in large part to have been a deficiency of compelling parametrizations of manifolds that has hindered their descriptive set theoretic study thus far. If you've ever thought about this a little bit, you've perhaps gotten annoyed that it isn't easier to parametrize manifolds. These are things that are appealing to the mind. And it's a little frustrating that there's no obvious, sufficiently general way of parametrizing them. What's ultimately wanted is an approach to the parametrization which is sufficiently versatile to accommodate the multiplicity of manifold structures arising in practice. We've seen a number of different kinds of manifolds, but sufficiently precise not to confuse them. Transparency facilitating such analyses as underlie the theorems above is, of course, of value as well, and perhaps this paper's most fundamental contribution is a parametrization framework which does meet these criteria. We introduce the notion of a Borel pseudogroup, and we prove the following. So any Borel pseudogroup G on a locally compact polar space X induces a standard Borel parameter space M, G, X of all Gx manifolds on which the relation of Gx equivalence is an analytic equivalence relation. We have prominent examples, by way of which we have straightforward and even in some sense functorial parametrizations of topological smooth and hyperbolic n-manifolds. So let's define our terms. Are there any questions? I'll start to give definitions now. Okay. So a pseudogroup on a topological space is a set of homeomorphisms between open subsets of X satisfying the following conditions. So we have X. X henceforth will be a locally compact polar space. You have open subsets, and you need the domains of these elements to cover X. You need the restriction of any element to an open subset of X also to be in G. The composition of any two elements. Even if the range isn't all of the domain, you have partial compositions. This will also be in G. So you have these closure properties. And nobody's asked me what a manifold is yet. That would be a fair question. But I want to put on the board the textbook picture, which is something like this. I'm not sure this is even worth turning on the light for. You all know what I'm going to draw. We have some open sets. And we have some maps. This might be, well, I'm not, this might be V. So this might be phi V. This might be U. And this might be phi U. And we have this overlap here. And the overlap is related by, well, if I want to map from here to here, I could take phi V, phi V after phi U inverse, and that would take me from this overlap to this overlap. And the question is, where does this live? And we're going to ask that this is in our pseudogroup G. I could just ask that this is a homeomorphism, but I could also ask that it's a diffeomorphism, or I could also ask that it's an isometry. And by varying these conditions, these requirements, I define different types of atlases defining my manifold. And so the pseudogroup is a way of parameterizing that. Pseudogroups on any topological space are naturally ordered by inclusion. These are subsets. This ordering possesses both a maximum and a minimum element. So the collection of all homeomorphisms between pairs of open subsets of X, this is the maximum. The collection of just identity maps on open subsets of X, this is the minimum. So if I say, I want this to be a homeomorphism, okay, that's a very generous requirement. If I want this to be a diffeomorphism, I'm restricting my pseudogroup. Any collection of homeomorphisms between open subsets of X falls in some unique minimal pseudogroup, because we have to restrict everything. So you have some collection of homeomorphisms, and then the closure properties will generate for you a pseudogroup. In particular, any group G of homeomorphisms of your ambient space, your model space X, may then be said to generate a pseudogroup, and we denote this by a sans serif G, and these form a prominent class of examples. Okay, so you don't need to read all the words here. What we have, I'll point the words that I want you, I'll just point at the words that you should read. We have Rn, or we have Cn, or we have hyperbolic space, Hn, or spherical space, Sn. You can put a topological pseudogroup on any of these guys. You could put the pseudogroup of Ck diffeomorphisms on these guys, k up to infinity. You could have the holomorphic pseudogroup, or biholomorphic pseudogroup. Or you could have the isometry pseudogroup, or the orientation-preserving isometry group. These are all standard and important pseudogroups. Now, here's our definition of a manifold. So the standard definition of a topological n-manifold may now be phrased as a second countable Hausdorff space possessing an atlas of charts whose transition maps all lie in the topological pseudogroup on R to the n. So to define other sorts of manifolds, we simply vary the pseudogroup appearing therein. So let M and X be topological spaces, and G a pseudogroup on X. So this is just the picture. I'm just giving you the definition of the picture. one of the things that's not, so this is M, and then it's equipped with this apparatus here. One of the things that's not clear just from the picture is that M is going to be Hausdorff. So we'll call M a locally GX space if it's endowed with a GX atlas, something like that. If we also want this to give us a Hausdorff quotient, then it's a GX manifold, and second countable. Okay, so the topological smooth and complex n-manifolds are precisely the first part's the pseudogroup, second part's the model space. In some ways, this part's a little boring, but we have to do it, and then I'll give us more interesting theorems in a minute. Euclidean spherical and hyperbolic n-manifolds are, again, within this framework. You can write it this way. Manifolds with boundary fit into this framework by you take the upper half plane, including 0. And, okay. So, what we have now is the parameter space as a set. I'm describing you for you the parameter space as a set. The parameter space of second countable locally GX spaces. Now our manifolds are going to be the Hausdorff elements in here. You have a family of open sets Uij. So if this had been U sub I, and this had been U sub j, then this would be U sub ij, this would be U sub ji, and this map would be phi ij. And what you might want to do if you want to parameterize this, you say, okay, well, a manifold is a set M endowed with these charts, which is a collection of open sets out in the space that you're modeling it on. That's X. And then these charts, these transition maps, which fall within the pseudogroup. But this set M is just a placeholder. You don't need it. You can drop M, and once you have these guys, you just take the equivalence relation induced by these transitions. You take the quotient of these open sets by the equivalence relation, the closed equivalence relation induced by these guys, and you get the manifold M. So the proposal is just to parameterize by a countable list of these open sets and a countable collection of pseudogroup elements mediating between them, gluing them together. And that's all that's happening here. So this is the set that's going to give us the parameter space, but we also need a topology on it.
Can you break that one?
Sure. So this is ensuring that it's an equivalence relation.
So how do you say the things are equivalent?
I guess the way I think about it is you just take the direct sum of all your U sub i's, and then you have an equivalence relation where x in ui is equivalent to y in uj, if and only if one sits in the image of the other by phi ij. Okay, so I think everyone knows this. The Fell, or Chabauti, or geometric topology, depending on your community, is the collection of closed sets of a locally compact Polish space. Okay, this topology on the collection of closed sets of a locally compact Polish space is generated by open sets of the form this and this. When endowed with this topology, f of x is compact Polish. And we topologize the set of open subsets of x by declaring complementation to be a homeomorphism. Being Polish, the Fell topology induces a standard Borel structure on both O of x and f of x, coinciding with the Efros Borel structure, for those that know. And for our purposes, the key point is that the basic operations, intersection, union, things like this, these are all Borel measurable. So going back to our definition, we're taking things, so the first bullet here, okay, so we're going to want to put a Borel structure on this parameter space. Now these are open sets. This is a sequence of open sets. So this lives in O of x to the n squared. And the next slide just gave us a Borel structure there. But we need to know how to think about these to endow this thing with a Borel structure. And that's where That's where Borel pseudogroups come in. So a pseudogroup G on X is Borel if it's endowed with a standard Borel structure such that each of the following maps are Borel. Now, some of these are redundant. You don't need to internalize all of them. A topological group is one in which the fundamental operations are continuous. This is the same thing for a pseudogroup at the Borel level. And then we have the fundamental theorem, which is the following. If G is a pseudogroup on a locally compact polar space X, then this parameter space inherits a standard Borel structure. The parameter space of Gx manifolds is the space of pairs such that M sub Ux, in other words, the manifold which is encoded, the manifold which is a quotient of the things given by U, comma, C, is a Gx manifold, or equivalently, is Hausdorff. And so you have to check, and this is irritatingly non-trivial, you have to check that Hausdorff is in fact a Borel condition. It is. This defines a Borel subset of the parameter space, which we denote by M of Gx. And so M of Gx is our space of manifolds. And the natural notion of equivalence, which encodes isometry or homeomorphism or diffeomorphism of two manifolds, this, in general, is analytic. That's not hard to show. And the pseudogroups that you would most immediately want to check are Borel. So they all fit into this framework. Moreover, the obvious restrictions of attention to compact or to connected or in metric settings to complete manifolds, these each define Borel subsets of this space of manifolds. From this and the fact that there are, for any n greater than or equal to 0, only countably many compact n-manifolds, this is Cheeger and Kistler, and this is a nice pigeonhole argument. You assume, there's like 5 pigeonhole arguments in a row. If people have students asking about the relevance of pigeonhole arguments, this is a good place to send them. There are only countably many compact n-manifolds. But if there's only countably many compact n-manifolds, then from the fact that the relation of equivalence is analytic, but we only have countably many classes, we then know that each of these is Borel, and that gives us a Borel reduction to equality on the natural numbers. It also gives us the following. Any assignment of invariance, whether Euler characteristic or homotopy groups, etc., to compact topological manifolds is a Borel operation, because you're just sending countably many classes to a countable set. So we just proved theorem A. And this also tells us that the locus of more substantial complexity must be non-compact manifolds, or more individually, the non-compact parts of manifolds which are their ends. So if we go back to theorems B or C or E, what's going on in those theorems is that strange things, interesting things are happening in the ends of those manifolds. So I want to jump ahead to theorem E. Okay, so in some ways this entire work with Ian traces back to when I first heard in Morelia the following theorem. Now this theorem traces to Carto, forgive me, but Richards in '63 is generally credited with its first complete modern proof. So two surfaces, X and Y, are homeomorphic if and only if they have the same genus and orientability class, and the triples of spaces like this are equivalent. What are these triples of spaces? They encode the space of ends of X. And the important thing for an audience like this one is that each element of the triple is a compact, totally disconnected Polish space. And two such triples are equivalent if there's a homeomorphism between the spaces of ends, which restricts to a homeomorphism on each of the two spaces, two subspaces. Already in 2011, Clinton Conley had noted on Math Overflow the connection to Camerlo and Gau's result that the homeomorphism relation on the space of closed subsets of the Cantor space is complete for countable structures. So for anyone familiar with this territory, it's at least intuitively clear where this theorem is landing us. And more recently, last year, Hoganson and Zombeck proved a version of theorem E for surfaces endowed with Pants decompositions. That might be small. That says the equivalence relation of on the space of surfaces with a pants decomposition. People know what that is? So if you have a manifold like the one that I've drawn, a pants decomposition of it is a breaking down of it in a combinatorial way. If you did this, if you cut along these three blue loops, then what you would have up top, what would fall away into two pieces, are a surface with three circular boundaries, and below a surface with three circular boundaries, not unlike, up to homotopy, not unlike the pants that any of us are wearing. And the point here is that the assemblage of pants in a pants decomposition into a surface, this combinatorial information is, in some sense, all you need for homeomorphism, for the analysis of the homeomorphism relation. C infinity, okay, that's, that I believe is how Jen is writing what I would say is complete for countable structures. Is that fair? Some people say Borel complete. I'm not going to say Borel complete. Yeah, thank you. We're on the same page. But to each their own. We love all vocabularies. Okay, so our problem, the problem that Ian and I have, is that we don't a priori have such pants decompositions. We don't, what we have is just a manifold. And what we need more precisely is some Borel way of assigning pants decompositions to the elements of our parameter space. Okay, so for this we needed a Borel, we dread it. We said we did everything that we could not to have to take this path, but I think you just have to take this path. We had to prove a Borel version of the Jordan-Schoenflies theorem, which is essentially this. There's a Borel measurable function which takes any embedding of S1 into R2 to a self-homeomorphism of R2 which extends this embedding. And then from this, you have a Borel way of assigning triangulations to these, to surfaces. And this was probably the most annoying part of our work, but there was no getting around it if we wanted to prove theorem E. But from this, then we have theorem E. So given a manifold, for its analysis, you want to be able to get your hands on it more combinatorially. This is a triangulation. Two manifolds, let's just recall, two manifolds admit triangulations, three manifolds admit triangulations. In general, above, it's not, you can't count on them. But even having them, there's a question of how do you get them? And whether you can get them in a Borel way. For example, I don't myself know how to triangulate three manifolds in a Borel way. But Martina Ianella does, and by way of this, she and Vadim Weinstein have proven the three-dimensional version of theorem E. So I believe, please correct me, Martina, if you're in the audience, I believe that this is the correct statement of their theorem. So the classification of connected topological three manifolds up to homeomorphism is complete for countable structures, as is the classification of connected smooth three manifolds up to diffeomorphism. So again, put differently, each is complete for Borel equivalence relations induced by Borel actions of the infinite permutation group S infinity. Okay. So in some ways, this is more impressive than our theorem E. So we had an off-the-shelf theorem, the Karatarko-Richards theorem, and we just had to get there with the Borel triangulation. In this case, Ianella Weinstein, I don't believe there was a classification theorem for three manifolds before, so they had to do that, but also had to do the triangulation. I also feel we got really lucky because Ian and I were thinking about this at the same time that Martina and this stuff at the same time that Martina and Vadim were thinking about it, i.e. over the past few years. And we could have ended up proving the same theorems, but we actually proved complementary theorems. I'm happy about that. But where does this leave us? So we know the story for homeomorphism and for diffeomorphism in dimensions 2 and in dimensions 3. What about 4? I don't know. A question that I know Foreman has advertised in the past is the question of the classification of smooth structures on R4, which is a 4-manifold. There are notoriously uncountably many, and it's natural to wonder how complex is this? I think multiple people have thought about this. This is a sub-instance of the question, just how complex is the diffeomorphism relation for smooth 4 manifolds and 5 manifolds and so on. So you could keep going up through dimension. And you could ask about diffeomorphism, or you could ask about homeomorphism. You could also ask the question, right? Because so we had the same benchmark complexity at 2 dimensions and at 3 dimensions. As you go up in dimension, does it get harder? Is it a strictly increase? I mean, so there's actually a case, which I hope we'll see, in which as you go up in dimensions, things get easier. So a number of questions ensue. A number of natural questions ensue. But you could be terrified by 4 manifolds, and you might just change the subject. So let's change the subject. So let's G be a locally compact Polish. Are there any questions at this point? So let's let G be a locally compact Polish group. Okay, then again, this is a locally compact Polish space, so we can talk about the Feld topology, and the closed subgroups of G form a closed subset of f of G. The set of discrete subgroups of G is open in this space of closed subgroups. The set of torsion-free subgroups is closed. What I'm getting at is all these guys are nice and Polish. And G acts on each of these guys continuously by conjugation. Okay. And this conjugation relation on discrete subgroups of G will write E of G comma D of G for the induced equivalence relation. And I want to note also for future reference that for G as above, the space of finitely generated discrete subgroups, I don't think we can expect this in general to be Polish, but it's a Borel subset, which is good enough. Okay. And some background. So F2 denotes the free group on 2, non-abelian, free group on 2 generators. So in 94, Stuck and Zimmer showed that E of F2, D of F2 is not concretely classifiable. In other words, it's above equality on the reals. And then they extended this result to any non-compact semi-simple Lie group G. And then in 99, Thomas and Blichkovich strengthened this result by showing that the F2 part is in fact at the level of E infinity. It's universal Sieber. And then in 2001, you had Andretta, Camerlo, and Hjorth. Okay, so they extended this also for any countable group G containing F2. And it's maybe more of a confession than I want to make when we started thinking about these things, but Ian was a postdoc with Simon Thomas. And among the questions that Simon, I think, threw at Ian, one of them was this. I would entirely credit this theorem to Ian. It rounds out the picture. For any non-compact semi-simple Lie group G, this relation is Borel bireducible with the infinity. This is the discrete, yeah. Okay. So this rounds out the picture, and it carries 2 main and related implications.
Is it for F2? Is it all
Yeah. So, yeah. You'll see why I care about discrete in a moment. So the first implication of this is that the following question becomes interesting. So given a non-compact semi-simple Lie group, what is the Borel complexity of E, D of finitely generated G? Notice this question is not interesting at this stage, because the finitely generated subgroups of G, well, there's only countably many. If we're working with a Lie group G, there's at least the possibility that we'll have uncountably many classes, conjugacy classes, of finitely generated discrete subgroups of G. And again, this is a question that traces to Thomas, and one way of thinking about this is, in all these theorems, the troublemaker is F2. You're just finding F2 in more and more situations. The troublemaker is F2, and F2 is weird in a number of ways. One of the ways that it's weird is that it has infinitely generated subgroups. One way of thinking about this question is, what if you screen out those infinitely generated subgroups? Do you still get high complexity? This is an interesting question. A related second question, or a related second implication of the theorem above, is the following corollary. The classification of connected, complete, hyperbolic, n-manifolds up to isometry is Borel equivalent to the degree E infinity for any n greater than or equal to 2. It might not be obvious, probably isn't obvious, why this is a corollary of the preceding theorem, theorem I. But it follows from theorem J. So if you look at isom of Hn, this is a Lie group. And if you look at a discrete, so we have Hn, which maybe looks like this, and then you have isom of Hn, which acts on it. And then if I take a discrete subgroup, well, then I can talk about Hn, the quotient of Hn over gamma, and this will be an n-dimensional, a hyperbolic n-manifold. So we have a correspondence between the discrete subgroups. So we have one direction of a correspondence between the discrete subgroups of isom of Hn and hyperbolic n-manifolds. And in fact, this arrow goes in two directions. If you're given a hyperbolic n-manifold, such as this one, then you could, it's called the developing map, you could unroll it onto its universal cover, and the fundamental group, then that will give you a representation of the fundamental group in this space, this group, isom of Hn. And that's what underlies this correspondence here. Theorem J gives you a correspondence between the conjugacy relation on discrete subgroups of isom of Hn and manifolds that we find ourselves caring about. So factored through theorem J, this question that we had about finitely generated discrete subgroups of Lie groups, the conjugacy classes, that becomes this other question. What is the Borel complexity of the isometry relation on the space of connected, complete, hyperbolic n-manifolds with finitely generated fundamental group? What's interesting for me here is that this is a question which arose in a descriptive set theoretic context, that the only answers that we have, and these are partial answers, are totally manifold theoretic. The tools are totally geometric. So what I like about this project is we have traffic, we have dialogue, we have assistance in two directions. In the time that remains, I want to talk a little bit about our answers. So rather than say connected, complete, hyperbolic n-manifold with finitely generated fundamental group ever again, I'll just call such manifolds algebraically finite. And I'll just point out briefly in the next slide that you can impose finiteness conditions on groups. You can, and people do. And you can also impose finiteness conditions on manifolds, and these correspond. So if you fix n greater than or equal to, n greater than or equal to 2, and you let M be the quotient hyperbolic manifold associated to a torsion-free discrete subgroup of the isometry group. Okay, so we can say that M is closed, and then we would say, from a group theoretic perspective, we would say that gamma is co-compact if M is compact and without boundary. We also care about M of finite volume. In that case, we would call the corresponding gamma a lattice. There's also a notion of geometrically finite. There's a notion of topologically finite if the manifold is homeomorphic to the interior of a compact manifold. And then there's algebraically finite, which is ultimately a group condition. It's just saying that the group is finitely generated. Now, these conditions are of weakly decreasing stringency. For each n, the classes of n manifolds associated to these conditions are non-decreasing in size. In other words, 1 implies 2, implies 3, implies 4, implies 5. For dimensions 2, for two hyperbolic dimensions, 3 and 4 and 5 are equivalent, and you can't reverse the arrows from 2 to 3 or 1 to 2. For dimensions 3, 4 and 5 are equivalent, but that's a fairly recent theorem. That was proved around 2007. So these are subtle conditions. And for each of these dimensions, we'll compute the complexity of the isometry relation on each of them. So in two hyperbolic dimensions, okay, so let's recall number one, that discrete subgroups of PSL2R are called Fuchsian groups, while discrete subgroups of PSL2C are called Kleinian groups. And I think I'll have to black box this equivalence. There's a really lovely topological isomorphism between this and PSL2R. And what I'm writing is the reason that people care enough about these discrete subgroups to have given them names. These names are due to Poincaré, and he named the Fuchsian group. I guess Klein was mad that the Fuchsian groups got that name, and then Poincaré tried to make good with Klein by naming the next one's Klein, but Klein wasn't satisfied. Seems to be how the story went. But the name stuck. So, in two dimensions, we have the following theorem. The orientation-preserving isometry problem for any of those classes above is Borel bireducible with equality on the reals. In particular, the classification of finitely generated torsion-free Fuchsian groups, etc., is Borel bireducible with the reals. Okay, so everything is equality on the reals. Everything is quote-unquote smooth or classifiable by countable structures. In particular, that F2 stuff was using something else at the level of PSL2R. Okay. In three hyperbolic dimensions, you get something more interesting. So for the lattices, remember that was the first two. That corresponded to finite volume. For the lattices, the complexity of the conjugacy relation is equality on the naturals. So actually, as you moved from 2 dimensions to 3 dimensions for finite volume hyperbolic n-manifolds, you went down in complexity. And what you're seeing there is actually most off rigidity. Then, at the middle level, you have equals on the reals. And then, for algebraically finite manifolds or finitely generated groups, it's E0. Okay, so you can say this at the group level. That's what I'm doing there. But you could also say it at the manifold level. And I want briefly to sketch what's happening here because it's the cutest part, it's the interesting part. So one path to theorem K is through the Teichmuller and moduli spaces of the relevant surfaces. Okay, so you have Teichmuller space, you have mapping class group, you have moduli space. This is the formal definition. It's also an informal definition. This is from Geometry and Topology of Three Manifolds by Thurston. There are, in fact, two important notions of equivalence giving rise to two spaces, moduli space and Teichmuller space. Informally, in Teichmuller space, he says, we pay attention not just to what a metric a surface is wearing, but also to how it is worn. In moduli space, all surfaces wearing the same metric are equivalent. And the importance of this distinction, he says, will be clear to anybody who, after putting a pajama suit on an infinite, has found one leg to be twisted. So summing up, the moduli space M of S parameterizes finite volume hyperbolic surfaces homeomorphic to S up to isometry. If S is given by n punctures of a closed genus G surface, then M of S is a polar space of dimension that. And essentially you're done for finite volume guys. By letting S range, you reduce isometry on finite volume hyperbolic surfaces to equality on a countable sum of polar spaces. You could also have infinite volume surfaces like this. They could look like this. they could have some end which flares out like a trumpet might, and that would be giving infinite volume. But then you can take what's called the convex core, and you can double the guy, and that will have finite volume, and the doubling will remember enough about the geometry of the original manifold to give you a weak reduction, and that's the idea there. So what's fascinating about this passage from 2 to 3 dimensions is how this template both persists and breaks down. This marked and unmarked thing. Okay. The central theorem in the territory of hyperbolic 3 manifolds is this, what Martin calls a blockbuster theorem, the ending lamination theorem. A hyperbolic 3 manifold with finitely generated fundamental group is uniquely determined by its topological type and its end invariance. As it happens, these invariants naturally array into a polar space, which is promising. Upon closer inspection, however, the theorem classifies marked hyperbolic manifolds. And a passage from these two are unmarked domain of concern is via a quotient by a group action not in general so nice as that of the mapping class group on type Muir space. Okay, so the heart of theorem L is the following, which runs counter to colloquial readings of the ending lamination theorem. Okay. You have a surface like this times R, and that gives you a 3 manifold. Those 3 manifolds, those hyperbolic structures on those 3 manifolds, E0 keeps showing up there. And one way that it does is via the shift space. So, quickly, this surface might have been a quotient. If you look at H3 as the interior of the compactification of C, then you have this plane, and then a quotient of gamma quotients this plane gives you this surface, and then the limit points of the action of this discrete group on H3 will show up as an equator here. But this starts to twist, and in the late 19th century, people were trying to draw these. I mean, you can conjugate by quasi-conformal transformations of the sphere, and then you start to change your group, and this will have different limit sets that look more like this that people were trying to draw in that picture. These limit sets can get more and more complicated until they fill up the sphere. And those hyperbolic 3 manifolds corresponding to a filled sphere, that's where E0 shows up. The point is that they're classified by geodesic laminations, and we have in proof 1 a result by Krestiski and Sabok that the natural action of the mapping class group on ending laminations, which is what classifies these manifolds, that this is a Borel complexity exactly E0. That's from that group. That's from that paper. And then there's another paper in which they actually coarsely embed the shift space into the space of hyperbolic manifolds. Okay, in closing, last slide. Well, plus an announcement. A descriptive set theoretic question about conjugacy relations took the form of one in which we answered in the n=2 and n=3 cases using fundamentally geometric tools. Now the question was this: what is the Borel complexity of the isometry relation on the space of algebraically finite hyperbolic n-manifolds? We don't have answers for any n greater than 3, in part because in those cases there's no comparable geometric theory to draw from. In the major survey of higher dimensional Kleinian groups, Kapovich writes there is a vast variety of Kleinian groups in higher dimensions. It appears that there is no hope for a comprehensive structure theory similar to the theory of discrete groups of isometries, in other words, Kleinian groups and Fuchsian groups, of H3. I'll just note in closing for anyone looking for a project that this thing in italics is exactly the sort of perception which invariant descriptive set theory excels at making precise. Many thanks to the organizers for the invitation and to the audience for their attention and for any questions which any of you may have. And I'll just repeat the announcement from yesterday. Next year's Young Set Theory will be held at the University of Barcelona. That's there. And we are very happy to announce the tutorials will be James Cummings, Yair Hayut, Sandra Mueller, Zoltan Bidnatsky. Please help get the word out to the young. Thanks very much.